All right, today we are going to calculate theoretically what is the acceleration due to gravity here on planet Earth. This is a symbol for Earth, it's a circle we cross through it. We have Newton's second law of motion, F equals ma, or the force due to gravity equals mass times the acceleration due to gravity. We're concerned with the force of gravity. Newton also came up with this law of universal gravitation that explains the force of gravity between two masses. And it's related to how massive they are and how far apart they are. So it's directly proportional to the product of the masses and inversely proportional to the square of their separation distance. So we can calculate what the acceleration due to gravity should be by equating these two. It's like substitution in algebra, where you say, if this is equal to the force of gravity and this is equal to the force of gravity, they must be equal to each other. So here's what we're going to do. We will take the force due to gravity equal to mass times the acceleration due to gravity, and we will take the force due to gravity equal to g m over r squared, and do what we can algebraically with these. So like I said, they're both equal to the force of gravity, so they must be equal to each other. So the mass times the acceleration due to gravity equals Newton's universal gravitational constant times the mass of planet Earth times the mass of, some object that's resting on planet Earth, like you, okay, or any object, over how far apart squared. Anytime you see the same variable in the same place on both sides of the equal sign equation, it means you divide by that quantity, right? So like dividing both sides by m divided by m is 1 times the acceleration due to gravity. Just what we hope to do. Isolate that, right? We want to know what the acceleration due to gravity is in terms of all this. And then m divided by m over here is also 1. So it's just equal to 1 times the rest of that. G, the mass, remember, of planet Earth over r squared. Now, it doesn't matter how massive something is sitting on the Earth. Like you're not affecting the Earth's gravity. Right? You're within it, and so it's the mass of the Earth that's determining the acceleration due to gravity. How far apart is this mass from this mass? How far apart are you from the Earth? Because that's what we need to know, the distance between them. So if you're trying to calculate, like, what's the gravity field that I'm feeling right now here on the surface of the Earth, theoretically, we would need to know the distance between those masses. Does anybody have an idea about that? How separated from the Earth are you? What is this value? You might be tempted to say 0 before you look at what would happen if we did that. So like I'm standing on the Earth, I'm sitting on the Earth, so like I'm not separated from it at all, right? Like this is between me and the Earth is 0. But then when you divide by 0, your calculator breaks, right? You can't divide by 0, get an error message. So you might say, well, I'm separated from 0 distance from like this part of the Earth, but like there's a whole other world over there, right? The whole other side of the planet. So yeah, you might be 0 meters away from this, the crust of the Earth here, but then how far apart are you from this part of the Earth, or this part, right? It's like, okay, we need to do something about that. And luckily, there were brilliant mathematicians that thought about this centuries ago that came up with integral calculus to basically say, you can approximate all the mass of planet Earth to exist at its center. So you are separated from the Earth by Earth's radius, or mathematically speaking. So we're really just going to use the radius of the Earth here. Again, that's making an assumption that here's Earth. Oh, like, that's not Earth. Earth is blue. Earth's got to be blue. Green, I guess. Blue, yellow, green. Earth. Okay. We take all of the 5.97 by 10 to the 24 kilograms of Earth, that's how massive the Earth is, Take all those kilograms of Earth and we say that it exists here at the center, which is how far apart from you. Well, that's the radius of the Earth, right? So we can just sort of plug in the radius of the Earth to this equation. Because some of the Earth is farther away from you than like this part of it, it all kind of averages out to just make an assumption that all of the mass of the Earth exists at its center. So all this mass exists. What is the radius of the Earth? So the radius of the Earth is 6.371 million. Right? So it's about 6,371,000 of these down to get to the center of the Earth. Right? This is 1 meter. We need about 6 million of them to get to the center of the Earth. So that's how far apart you are from the Earth, theoretically speaking. Right? On average, that's how far apart you are from the Earth as you stand on the surface. So that's everything we need to crunch the numbers now, right? We can solve for the acceleration due to gravity. That's going to look like this. A box. The acceleration due to gravity equal to G. I'm going to write out my equation first, in variable form. Symbol for the Earth there. G has a value of 6.67 by 10 to the negative 11 Newton meters squared per kilogram squared. The mass of the Earth, I told you a moment ago, is 5.97 by 10 to the 24 kilograms. And the radius of the Earth is 6.371 by 10 to the 6 meters. Don't forget to square that. If you look at the units here, we've got meters squared, canceling these meters squared. We've got kilograms, canceling one of these kilograms. And so we're left with newtons per kilogram. Okay, but we're solving for acceleration. Is that a problem? That's around the computer monitor here. Is it a problem that we're getting newtons per kilogram units when we're solving for acceleration due to gravity, which we know the units of acceleration are? On the tip of everybody's tongue, let's all say it together now. Squared. Meters per second squared. So meters per second, right? We're looking at a change in velocity over a change in time. That's what acceleration is, right? So we're speeding up or slowing down as a function of time. We're changing our velocity as a function of time. Is this? Right? Like this is a base units type question. All right. Remember that according to that same Newton's second law, F equals ma. A Newton of force is a kilogram meter per second squared of acceleration. Right? That's what a Newton is. These are the base units of this derived unit. So if you substitute that in for a Newton over here, a Newton is a kilogram meter per second squared. So a Newton per kilogram is indeed a meter per second squared, right? It checks out. A Newton per kilogram is the same thing as the units of acceleration meters per second squared. In this regard, we think about, let's give it the known value. The Earth's gravity field can be thought of as the force that's exerted per kilogram. Okay, I'm 100 kilograms. There's 9.8 newtons of force acting on each kilogram of my mass, and so I weigh 980 newtons, about 220 pounds. Okay, so 220 pounds divided by 2.2 pounds per kilo. That's why I'm a nice even 100 kilos of mass. And it's a nice convenient way to think about my weight is just 980 newtons, right? Because I happen to have a mass of 100 kilos. You weigh 220, your mass is 100 kilos. So try to maintain that weight. So stay at consistent 100 kilos. But another way to think about that is that gravity accelerates things at 9.8 meters per second every second, right? 23 miles per hour faster every second something falls. We have that talking about it. But there are equivalent ways to think about it. Okay, the force per mass or the acceleration, meters per second squared. Now, what does the value work out to be when you actually crunch these numbers over here? Move the camera. Oh, actually, you can still see it there, right? So that's the one that we're looking at here. All this equals from the chalkboard to the whiteboard. And calculator. All right, ready, everybody? Here we go. 6.67 by 10 to the 6.67 by 10 raised to the negative 11 times the mass of the Earth times 5.97 by 10 to the 24th. Okay, divided by 6.4 million thereabouts squared, so divided by 6.371 by 10 to the 6th squared equals, all right. That's a really good answer. Anybody doing this following along at home? YouTube? What is it? Right, exactly. Leave it down in the comments. 9.81 meters per second squared. It works out exactly there. Now, we should maybe say that we're assuming Earth is a perfect sphere, that this is a constant sort of acceleration of gravity everywhere, and that's not true. There are more sophisticated equations to account for like what latitude you're at. Earth is an oblong spheroid where the poles have been sort of pushed down, so Earth is fatter at its equator. There's more distance from the center of the Earth to the equator than there is from the center of the Earth up to the north or south pole. So this change is depending on sort of slightly depending on where you are on Earth, you know, your elevation, your latitude, and so on. But we can just say, well, pretty much constant anywhere on Earth's surface. And that's about that. So that's where the number comes from theoretically. It comes from how massive the Earth is and how big it is. The bigger planets are, or stars, and things creating a gravity field, the more that gravity is sort of like spread out, so it becomes weaker, right? Like a big planet, we're dividing by this, you know, square, right? So bigger numbers here, which are bigger planets, right? Bigger radii, have weaker gravity fields by virtue of the fact that they're bigger, because they're spreading their sort of mass out over more area. But they're all bigger planets also tend to be more massive too. And so like you say, well, what about a planet like Jupiter? Jupiter is way more massive than the Earth, but it's also bigger. So which one sort of wins? It turns out that Jupiter's gravitational field is about 23 meters per second squared. So it's a stronger gravity field than Earth because it's a lot more massive. So even though it's bigger, that term doesn't dominate sort of when you compare it to Earth. The sun is like huge. We can do the same thing. Okay, we can calculate it the same way. So this is a very, it's a general equation allows you to calculate the gravity field anywhere, right? You know how massive the thing is, creating the field, you know, sort of its size, all right? And then you can theoretically calculate what the gravity field should be, and we can do it for Earth, and we can see the degrees of what we determined experimentally. No, this has nothing to do with dropping marbles or swinging pendulum, okay? So this is just sort of a theory that says, well, massive objects create gravity fields, and then other massive objects move through them, you know, a certain way. They're attracted to them via this equation. All right, so that's what we're going to kind of look at today with projectile motion. So let's move it over here. All right, so let's put some values up on the board here. All right, today we're going to launch. And we want to predict the height, 1/2 g c squared, and we want to calculate the range. T, where T is the total time in air. Range is the horizontal distance. Our vector, we can break down into a y component like this. An x component here. The blue is our actual trajectory. Okay, that blue vector there. We're launching at that, along this blue path with some angle theta above the horizontal, and we know that we can resolve the vector into x and y components. So there's the velocity v, the blue vector, which will resolve into the pink vector, the x, which is related to the range. So the range is the x component of displacement. The time is really dependent upon the y component, right? Like how fast we launch this. And a further sort of complication is that with our marble launcher, we are about 26 centimeters above the lab bench. So see how we're assuming we're landing at the same elevation that we're launching from. But if we consider the apparatus here, okay, this is what we're using to launch. It's 26 centimeters above the lab bench. Okay. So we could either consider camera person. Should have turned on the intern. Got me the intern this game. Camera person. We could say, well, let's just calculate it's falling an extra 26 centimeters. We know physics, we can do that. Makes it tougher, right? Like we're just sort of saying, well, we could just use this to solve for the range of its equal elevation. But what if it has to fall like an extra 26 centimeters? Like what if we launched off the edge of a building? We let it fall all the way down. Couldn't we calculate like how far away from the building it would land and how much time it would be airborne? Yeah, sure, we could do that. But it's a little bit tougher. Instead, we should just try to like make it so that we can land at the same elevation. So the marble launcher is 26 centimeters, right? Which is 0.26 meters. So I have a 0.26 meter tall box, 26 centimeter tall box. And if we're sort of launching from that high up and just sitting on the table that high up, then we're landing at equal elevation. We're pretty close, right? We'll get the bullseye. All right, so that's the idea. Previously, we've found that we can launch a marble at, remember, the marble was what, 1.8 or 1.9 centimeters wide? And we have that in your notes. So here we've got pretty good. 1.9. See how the marker is just before the 2, the 0 sort of line. So 1.9 centimeters is the width of the marble. And as we send the marble through our photo gate timer, you can see how much time it would take a 1 point. How much time would it take a 1.9 centimeter marble to break the plane of the photo gate? How much time? 0.0023 seconds. Okay, 0.0023 seconds. Just like that plane. Like that. So the velocity is the velocity is 0.019 meters divided by 0.0023 seconds, or 8 point something. Calculators around 0.019er divided by 0.0023, 8.26. We're launching at 8.26 meters per second today. What angle? What angle do y'all want to launch at? Right now it's 35 degrees. So if you just witnessed that, was a 35 degree launch. I'll go higher. Now here's a problem. Kinematics, right? This is all kinematics. It's just studying motion without regard for what's causing said motion. We're not accounting for any forces besides gravity. Gravity is affecting the y component of velocity, right? It's slowing it down to a stop, speeding it back up again. We're not accounting for forces like the ceiling. Okay, which will exert another force on its change of motion. So that was a launch angle of 80 degrees, pretty steep. So keep that in mind, right? We would have to sort of do, okay, the ceiling exerted a force, change its trajectory, right? So that object remains in motion until an outside force acts upon it. And the ceiling was definitely an outside force there. So 80 might be too steep unless we launched at like a slower velocity. So we could calculate like, and I know you all have a table sort of there. We're just sort of double checking those. So this is like notch 2. So that's a much slower speed, right? So it's not going to go as fast upwards. And so it's not going to be airborne as long. It's not going to go as far down range, right? So the two things that affect the range are the Vx and the T. The x component velocity of time. So okay. Let's choose a sensible launch angle here. 50 degrees. At 50 degrees, would you predict this number or this number would be bigger without calculation? Would the y component or the x component be bigger if it's a 50-degree launch angle? Say it again. Would be greater? That's incorrect. So somebody else then, right? It's like Jordan gave me a good little alley-oop there, so we slam dunk that thing down. Got to be the y component then, right? And so it's okay to say like, oh, okay, yeah, I mixed them up. If it's greater than 45, right now in your calculator, do cosine 45, sine 45. Like let's say cosine 45 degrees equals, look at that number. Where do that right? Cosine 45 degrees. Everybody, I'm part of it. So I say cosine 45 equals, and I get a number 0.7071670. That's, I think, the square root of 2 over 2. If you take math class, you're like, there's an exact value, like decimal approximations here in physics, okay? Now do the sine of 45. Can you see that? What do you realize when you do that? They're the same. So bisecting a 90-degree angle, you're perfectly splitting the x and y components. That maximizes range, okay? Because we're going as fast as we can up, which maximizes t. We're going as fast over as we can, which maximizes x, the x. And those are the two things that we multiply to get range. So when we have angles steeper than 45, right, which I said 50, it's a little bit steeper than 45. So we'd say, okay, more of the motion is upwards then. So any angle greater than 45, this number should be bigger. Any number less than 45, this angle should be bigger. It's like we're launching at a shallow angle, which means if I launch at, say, 30 degrees. This is a shallow launch angle. Three, two, one. Did it hit the ruler there? Awesome. Anyway, that's besides my point. It's a shallow launch angle, okay? Things can go far down range because they're going really fast sideways, right? Vx is pretty fast. And that's true when you put most of the angle horizontally, like we just saw, like 30 degrees is a shallow angle. It's less than 45. So it didn't go up that high because it didn't have as fast of a y component, but it was going fast this way. So one way to get downrange is to be going really fast sideways, like a baseball pitcher. They don't really throw the ball up in the air, right? They just throw it really fast this way, right? So it goes downrange because it's going fast this way. The time is really dependent upon their height and the height of the pitching mound, right? Like however high up they are, gravity acts on it. If you fire a bullet out of a rifle and you drop a bullet from the same height, they hit the ground at the same time. The bullet's just much further downrange because it's going faster this way. But the time is just dependent upon how high up they are. Okay, so that's something that's true. So we would expect that things that have steep angles, they go downrange because they're airborne longer, right? So they're not going so fast this way, but they're airborne longer. And so if we launch something at, let's say, 60 degrees, this still might be too steep to get us underneath the sun. If we launch something at 60 degrees, which is, let's see. Let's go back to that original 50. 50. So here's 50 degrees. And now here's 40 degrees. Any observations about that? About the range, let's say. Anybody notice anything about the range of both of those launches? They're about the same, right? One went faster sideways, but wasn't airborne as long. That was this one, the second one. It was 40 degrees. The first one, 50 degrees, didn't go as fast sideways, but it went up higher. So it had the same range. I'm going to test 70 degrees, but at a slower speed. So this is going to be a steep launch angle, but it's not going to hit the ceiling, okay? Because we want to actually see the trajectory. So here's 70 degrees. Like about here. You saw how high up it went. Here's 20 degrees. Just to really emphasize, like 50 and 40 are pretty close, but what do they add up to? 90, they're complementary angles, right? 70 and 20, also complementary angles. There, that one there went about the same distance, but it didn't go up as high. It was traveling more quickly sideways. Okay, so here's sort of I don't want to lose my marbles. Just throw it over. We got to really work on our projectile motion physics here. We're understanding. Oh wait, yeah, outside forces. Yeah, we're prepared to deal with that. All right, one more time here. Right there. All right. So complementary angles lead to the same range. I could test 45 and 45, but hopefully you'll sort of know here that it would give us the same number, right? So like, because the cosine and the sine of 45 is the same value, when we multiply that number, 0.707 by 8.26, we're going to get the same x and y components. And so, we're going to get sort of the same range. 45 and 45 are complementary angles, right? So that's kind of like, yeah, we test the same angle twice, we should get the same range. But any complementary angles, 60-30, 50-40, 70-20, 80-10, they will give you calculations that give you the same range, because the steeper angles will just sort of maximize t, and the shallower angles will maximize dx. But they sort of perfectly work out to give you the same range as long as the angles you choose are complementary. So we want to test 8.26 meters per second at an angle, calculate the range, calculate the height, okay? And then the game that we can play with this is to have you all calculate what the range would be, and then give you different points for different receptacles. So this is the way that we sort of traditionally play it. We could do that or not. We could just sort of, launch marbles and say, well, let's test this one, and just so we'll all be on one team, or you guys can make teams. So the way we traditionally play is like, if you can make it in this receptacle, that's like 10 points. If you can make it in this receptacle, it's like 3 points, or let's make it 5. 10, 5, and 1 point, if you make it like inside the box, because it's a bigger sort of target there. And then you'll find that if you do some calculation, you say, okay, I'm going to launch at 38 degrees. Let's do that real quick. What would happen if we launched at 38 degrees? Well, the y component of motion, the initial y component, is going to be the sine of that 38 degree angle times the 8.26 meters per second of velocity that's delivered. And so the initial y component is I'm getting 5.09. Check it again. That's sad. Yeah, but you can't beat me with the calculation. No one's beat me yet. It's not going to be today. Check it again. Sometimes I just have to drown the student's voice out. Students start to call the answer. I'm like, I don't hear you. Oh yeah, 5.09. You can do it. Still got my record. Say, no, that's okay. For a long time, I maintained my undefeated streak in chess. So I could keep a chessboard in the lab, and anytime someone wants to challenge me with a chess match, I saw the other days when it came in. So I one of my students came in, challenge me with a chess match. Challenge accepted. Okay. But a few students have beat me, so you can see up on my wall of shame over there. It's like I got all my degrees, so that's kind of cool. But then above that, you got the way to go. Those are the few times I've lost chess. Okay. So give a student a nice little way to go certificate for that. More valuable than a diploma. Okay. More valuable than a high school diploma, in my opinion. Okay. So you got 5.09 for this one, and then what's it going to be for the VX? And now I said 38, so we say, oh, that's less than 45. I would hypothesize whatever number I get here to be less than 5.09. And that one's going to be the cosine of 38 times the 8.26. All right, ready? Everybody has a fair chance. Go. So we got 8.26 there, and so no one was able to find out before me that the answer is 6.5. Well done. 6.5 we did that. Which is greater than this because the angle is more shallow, right? So if more of the velocity is directed towards the x direction, it should be moving faster that way, right? So anything less than 45 is going faster side. So now we can use this to say, well, when would gravity slow it down to a stop at this point? So we always consider a point like at the top of its flight, where the velocity goes to 0, and the velocity is equal to the initial velocity plus acceleration times time. So 0 equals 5.09 minus 9.8t, 9.81t. So this is using this equation of motion to say, we know what it started out at in the y direction. We know gravity only affects things in the y direction, acceleration due to gravity in the y direction. So we're only considering the y component of motion with the green chalk. Okay. That's our initial velocity vector this way. That's the direction that the acceleration due to gravity is acting down. So it's negative, right? This is positive 5.09. We launched it positive 5.09 meters per second. So gravity is opposing it, negative 9.81. Do not subtract 9.81 from 5.09 right now. Don't do that. Because you would never do that, you know, like this. Say you had this math problem in algebra class. You wouldn't go 2 minus 6 is negative 4x, hopefully. You say that term is unlike this term. They're unlike terms, I can't combine them. Rather, you would subtract 2 from both sides, and then divide both sides by negative 6. Sometimes it's helpful to give yourself like an x instead of a t for some reason for high school physics students. They're like, t, we can't solve for t. Like, how about x? Oh yeah, x, we solve for x, we do that all the time. But, turn the t sideways. You know, so, and I'm only halfway joking because sometimes it is just like, it looks more familiar to us this way. But it's like, well, the x is just some variable, right? Like there's some unknown. What's unknown is t right now, time, t for time. Call whatever you want to. Smiley face, I don't care. That's what we're solving for. We got to do the algebra right. So the algebra doesn't say subtract like 6 from the 2. That's connected to this variable, right? The term here is 6 times x. That's the order of operation. We're going to multiply that first before we do the subtraction. So here we're going to subtract 5.09 from both sides, which would be negative 9.81 t. And then we divide each side by the negative 9.81. That's how we get our time positive again. Time should be positive. So yeah, the negative divided by a negative is positive. Right now, as we do a bunch of these calculations here today, just think computationally. I can solve for the time, the max height, as just the initial y component of velocity, which is just the sine of the angle times the speed, divided by 9.81, right? That's computationally what it turns out to be. But it's not, I don't think it's a good way to teach it, to just say, here's an algorithm to calculate things. Take a number, take the sine of it, times it by this, divide it by 9.81, without like seeing why do I do that? You know, it's because, hey, we derived this whole equation of motion. We said that always works to kind of relate these things. We know 3 things about it. We can solve for the 4th. Algorithmically, or just like purely computationally, yes, it just boils down to take this number and divide it by a graph, right? Then you solve for the time and max height. So the time is the initial velocity divided by the acceleration due to gravity. So for this one, it would be what's 5.09 divided by 9.81? It's about half, right? It's about half a second. What do you get when you do that? 5.09 divided by 9.81. 0.52. So this thing should reach maximum height. After 0.52 seconds. Which means it's going to hit the ground, hit the top of our box, rather, after 1.04 seconds. Or we could calculate what is its half range. Okay, so range is just Vx times whatever time you want to know. You could pose the question like this. How far down range is the projectile after 0.1 seconds? Well, just, you know, it's Vx, plug in 0.1 seconds and you calculate how far it is there. How about after 0.2, after 0.3, after 0.52, right? So calculate after 0.52 seconds of time, if it's moving 6.5 meters per second sideways, horizontally, what is its range to that point? So the range, you're getting 3.4 meters. Which means the entire range would just be double that. So you could either double the time like I did here and then multiply that by Vx, or you could say, well, I just calculated the range halfway, and I'll double that to get the total range. You see how mathematically that's going to be the same, like either double the range or double the time, factor a 2 in there gets you sort of all the way. So 3.4 doubled is 6.8 meters of total range. And sure enough, if I did 1.04, times 6.5, I would also get 6.8, thereabouts, okay? So that's our prediction. Now for the height, we're going to use 1/2 gt squared. So where t is this 0.52, so it's like if we drop a marble from the top of its flight, how long would it take to hit the ground? That's the same answer as how much time did it take it to go up that high? Okay, so it's the same physics as our drop blast. So we'll calculate the height as half of 9.81 times the 0.52 squared. All right, we're just going to plug in this half time, right? This time that we get to 9.5. So we have 0.5 times 9.81 times 0.52 squared to get a height of 1.3 meters. Height is 1.3 meters according to this calculation. Okay. The range is 6.8 meters according to this calculation. So now we have some testable predictions. We will go 1, 2, 3.4 meters downrange. And we expect that at this distance, 3.4 meters downrange, the height would be 130 centimeters. And so we've got about there, then we can sum it. All right, so we've got now ruler set up so that the top of that ruler is 1.3 meters above the lab bench. We're going to place our, where did it go for it? We're going to go for the red cup receptacle. And we want it to be 1, 2, 3, 4, 5, 6.8. 6.8 meters away. Now, our equal elevation, so it's going to come in an angle and crack right here. So we'll just use that bullseye. I very much doubt that it will land on the bullseye because we'll find that theory and experiment, as you may recall from chemistry, they don't always agree, right? You do a theoretical yield, you do an actual yield, you do a percent yield, right? You say, well, theoretically, I should be able to make this much. When I weighed in my laboratory, I didn't. There were some losses there due to uncertainties and sort of things in the procedure that are hard to sort of iron out to eliminate those systematic errors. So the sources of uncertainty here really come from, I think, how each time that we launch this, it's slightly different. It's like a mechanism we're releasing that's crashing into it, and it's not hitting the exact same place, exactly the same force each time. And so, we could get pretty consistent velocities out of this, but even so, it's, like we're only accounting for like the up and over directions, but there's a third axis too. So like you could veer off course this way or that way. So trying to square all that up. So, all right, I think we're good to go here. I will keep the photo gate timer trained on it so that we could, like, for each one, if we say, oh, well, that one's way off, we say, oh, look. Sometimes just the way that you release the mechanism, you kind of catch on this, and so it won't sort of deliver as much energy each time. So for each trial, we'll be able to sort of take a look at the time data and see like, oh, was it really 8.26, right? Because if it's leaving there with faster, time or a slower time, then that means the velocity was different, right? Which would change obviously everything else that we base these calculations on. And then if we wanted to, we could recalculate, say, oh yeah, that's why it was this, or we could say, okay, let's pick a new one. All right, so here we go. 3, 2, 1. Happy about the height there. It was like a nice, almost perfect. But then it started falling short, right? It didn't quite make it as far as we predicted. And again, I kind of said that it really never works the way exactly what we think. So you might think, oh, it just landed here. There you go. It's going to land there again. Lightning will strike in the same place twice, but it doesn't. Like I said, it's uncertain. So when we play this game, like in years previous, and students are coming up here and they're moving around the receptacles, and this year it's slightly different. It's like, hey, move it here, it landed right here, move the box exactly right there. Now it should land there again, right? Oh no, we didn't move it as far as we needed to. Should have moved it to here. Now it's going to land there. And then the way we play is like you get 3 trials. And if you make it on the first one by some chance, you get like 3 times as many points. The second try is only worth 2 times, and the third try, that would be worth 1 time. And you see, each time it was a little bit different. 3, 2, 1. 0, 0, 2, 4. 0, 0, 2, 4 seconds. Okay, so that would have been what? A little bit slower. Okay, but 0.0001 seconds. All right, so this is how to sort of, one way to approach these calculations is to sort of consider this point that's 0, use your equations of motion, the same equation of motion, that we had derived. That can tell us about the y component, like the maximum height, and the x component, like the range, and sort of knowing how to apply those equations correctly. In general, the equation of motion that we're using here is the displacement equals ut plus 1/2 a t squared. Okay, so remember that this is, I think, what we call the equation 2. And we're saying projectile motion, the learning objective is students will be able to explain projectiles in terms of horizontal and vertical components of motion. And these equations work in all directions as long as, again, we're applying them correctly. So we could say in the x direction of displacement is called range. There's a special word for it. So that's the range just in the x direction now. Well, it has the initial velocity is the final velocity, right? Like that's, so the vxt, that's just like this. Okay, there's your vxt is solved for range. What happened to the plus 1/2 at squared? What's the acceleration in the x direction again? 0. So when a is 0, 0 times t squared times 1/2 is all 0. And that's why in x direction, you just get this equation. Just simplify it down to that. Remember, we have non-accelerated motion in the x direction. Non-accelerated means that term goes away. In the y direction, we do have accelerated motion, right? Gravity is an accelerator that only affects things in the vertical direction. So in that regard, that's when this goes to 0. Like we consider the object falling from this point. Okay, like if we drop it, then its initial velocity is 0. And so that term kind of goes away. So we said the displacement in the y direction, well, that's height. And so the height is equal to, if I'm just dropping something, there's no initial velocity. So that term goes away. And I just get 1/2 the acceleration due to gravity times time squared. And so it's the same equation where it's just like, in the case of the x component, it is the acceleration that is 0. So that term goes away. In the case of the y component, it's the initial velocity that is 0. So that term goes away. But what if it's not 0? what if we did have to solve for how much time would it take the object to fall the extra 26 centimeters? Okay. Could we possibly solve that? So that would mean that like we could use our range equation, but then once we got here, it'd be like it would be traveling at some non-zero velocity, right? Like we have to say, well, what's the extra bit of time that it would take to fall if we didn't have that box there, let it fall over the table, which it did in every trial, right? It never hit the box, always left it in short. So there, what we want to do is calculate to solve for time, okay? So let's consider just the y component, the one that gravity is going to act in. But this time, we're going to start with the initial velocity, okay? 5.09 meters per second. By the time it gets back down to that same elevation, you've given gravity just as much time to speed it back up. And so it's actually going to have a right at the same elevation. Okay, like right when we launch at 26 centimeters, it gets to 26 centimeters. Right at that point, there's a downward velocity vector of 5.09, just like it was up over here. So it's kind of like we're considering the total time airborne, t, but what would be the displacement that we should plug in for solving for t? The vertical displacement, 1.3 meters still, right? Oh no. The displacement is going to be the 26 centimeters. And this is what I mean. It's easy to sort of get, you know, it's like, well, wait, what am I solving for here if I plug this in? If we plug in 1.3, right, then we're saying like the time takes to sort of fall this distance. So let's consider now, we're 26 centimeters above the table, and that's going to be the net change in position, right? Displacement is the net change in position. So I'm starting 26 centimeters above the table, and it's ultimately going to fall 26 centimeters down. I'm going to do some other things in between. I'm going to launch it up in the air, let it travel. But in the end, it's only going to be 26 centimeters difference in the y direction. So here we have S equals UT plus 1/2 AT squared. We want to go 0.26 meters when the initial velocity in the y direction is 5.09. I want to know how much time it's going to take to go this net change in position. If I launch at positive 5.09, 1/2, gravity is still negative 9.81 times time squared. Okay, so how much time t will it take the object to travel to 26 centimeters vertically? Well, we have a perfectly solvable equation, right? Perfectly solvable. Let's write it like this, though. What's half of negative 9.81? Negative 4.905 t squared. This term is 5.09 t. 0.26. I'll drop the units for now, knowing that, you know, all the distances are meters, the acceleration is meters per second squared, so I'll be solving for seconds time. And then let's write it like this. Negative 4.905 t squared plus 5.09 t. And then subtract this from both sides, minus 0.26 equals 0. All right, why write it like that? Well, this is fun Friday. How else are we going to have fun unless we... Sorry. That's right. The quadratic equation. They just call it in. That's the phone a friend. It's a street shout out. All right. So if we need to solve for t, if I were to, again, make it a little bit more familiar to you, hopefully. You've seen something like this before. You said, oh, in math class, if I have a quadratic equation, I want to know this variable x, but it's like, it's attached to this coefficient a and it's attached to this coefficient b. It's like, hey, what number times itself times this number a plus that same number times some other number b, when you add this constant c to it, gives you 0. It's hard to think about what that number x would be, right? So for us, we've got a is this negative 4.905. B is this coefficient 5.09. T is like the x we're solving for. Remember, 15x is the unknown. And then our constant is the displacement, negative 0.6. So I forced it into what was a standard form of a quadratic equation. Why standard form? Because again, brilliant mathematicians have said, if you got something like this, here's how you figure out what x is. It's right? Everybody's learned x equals negative b plus or minus the square root of b squared minus 4ac over 2a. Quadratic formula, right? This is the answer to the question. When are we ever going to use this? Like you're in math class learning this, and you're like, x equals negative b plus or minus the square root of b squared minus 4ac over 2a. When am I ever going to use that? Like in physics class, we need it to solve for time. We're watching a marble. Okay, that's important. This is why we do it, right? We gotta know how to watch marbles. Okay, it's the heart of all the physics. So we can apply this quadratic formula to the equation that we just kind of, I mean, these are real numbers, right? It's like, you know, we actually are setting it at this, we measured this to be true, that's the speeds. So we should be able to solve it. All right. So it's gonna look like this. T equals, right? Solve for t. Negative b, so negative 5.09 plus or minus the square root of 5.09 squared minus 4 times negative 4.905 times negative 0.26 for AC, all divided by 2 times A. Got start underneath the radical here, so I've got 5.09 squared minus 4 times 4.905 times 0.26. Because they're both negative, I just know that like my multiplying is positive, but I'm subtracting this whole quantity 20. Or rather, I get the whole quantity 20.8 when I do that. Oh, maybe I do. 5.09 squared equals 25, so minus 4 times A times C equals. So I get underneath the radical 20.8. So I have 5.09 plus, and then I have to take the square root of it, so let me just raise this to the 0.5 power. So 5.09 plus 4.56 over, now if you double 4.9, negative 4.9, you get back to 9.1. Right, but that's negative. And then over here you have 5.09 minus 4.56 over, that's negative b, right? Negative b. Negative 5.09 minus or plus negative 4.96 over 9.81. So this one here gives you 5.09, negative 5.09 plus 4.56 is negative 0.53 divided by negative 9.81. So it's T equals 0.05 seconds. This one here would be negative 5.09. I feel like I made a mistake. Minus 4.56 divided by 9.81. So this would be 0.98 seconds. Okay. .09 squared. 25.919081. 4 times A yeah, 20 something, whatever. So you have one solution, negative 5.09 plus 4.56, negative 5.09 minus 4.56. So both of the answers actually come positive, right? Because this is still negative. So it should either take 0.05 seconds or it should take 0.98 seconds. All right, so those are the two solutions that we get, for the time here. We never want to solve something like this if we can avoid it, but it's worthwhile to do it, once in your life. And so you can actually see where the quadratic formula comes into play here. But by considering the motion of the object from this point, it's like it's dropped at an initial speed of 0, we could just break the motion down and go, well, how much time to get here? How much time at the initial velocity of 0? So this term goes away, right? To get the rest of the time. So there's different sort of paths to the solution as we mentioned before. All right. Think about you practicing these calculations so that when we take this apparatus back out, you'll have a hypothesis for, hey, I want to launch with these conditions. I predict I can put the receptacle here and see if I can get a bullseye. One more before the bell rings. And your quiz grade is based on this. So, say by the bell. Oh, we got it. We saw you too.